last class we are talking of the 3D tetrahedral elements, and we had seen the formulation for a general tetrahedral element consisting of 4 nodes. And then we are saying that if we have a cube, how we can split this cube into a set of tetrahedral elements. Okay, for splitting a cube into tetrahedral elements, we had considered a splitting mechanism like this, where we said that if we have this cube given by 1, 2, 3, 4, 5, 6, 7, 8, 8 nodes, and we want to split it into tetrahedral elements, we can take elements like 1, 2, 4, 5, 2, 3, 7, 4, 4, 5, 7, 8, that is 4, 5, 7 and 8, and 2, 5, 6, 7, 2, 5, 6 and 7, and the fifth one is 2, 4, 5, 7, which is inside all these 4 elements. These 4 elements are basically at corners 1, 6, 8 and 3. So if we cut off the corners, we will have a tetrahedral element in the center, that is this element number 5. And we said that if you look at the volumes of these 5 elements, the first 4 have a volume of V by 6 and the fifth one has a volume of V by 3. Okay, and if we want to get elements of the same size, that is, we want to have the same volume for all the elements, we can divide it in another way, and that is like this. If you have this 1, 2, 3, 4, 5, 6, 7, 8 as a cube, we can take a vertical diagonal plane. Okay, that means if we join 8 and 6, you can take this vertical diagonal plane and divide this cube into 2 parts, and then each of these halves I can divide them into 3 tetrahedrons each. Okay, if I take 1, 2, 4, 6, so 1, 2, 4 and 6, so 1, 2, 4 and 6. Okay, so this tetrahedron one, 2, 4 and 6 is one tetrahedron, 1, 5, 6 and 8. So 1, 5, 6 and 8. So I join this. This is the second tetrahedron, and 1, 6, 8, 4. So 1, 6, 8 and 4. This is the third tetrahedron which is obtained if I remove this 1, 2, 4, 6 and 1, 5, 6, 8 from this half. So this way this half will be divided into 3 tetrahedrons. Okay, so this is, let us say, my element 1, this is my element 2 and this is my element 3. Okay, so in these 3 elements, if I look at the volumes of each of them, 1, 2, 4 and 6, okay, I can look upon this triangle 1, 2, 6 as the base and 1, 4 as the height of the pyramid. So the volume of this will be V by 6. So V is the total volume of the cube. Okay, similarly 1, 5, 6, 8. 1, 5, 6 can be looked upon as the base and 5, 8 as its height. So the volume of this will also be V by 6. Okay, and 1, 6, 8, 4 will be 1 half of this cube, that is V by 2 minus V by 6 minus V by 6. So this will also be V by 6. So we will get 3 tetrahedrons, each with a volume of V by 6. Okay, similarly in the other half we will get another 3 tetrahedrons, each with a volume of V by 6. So this way we can split this cube into 6 tetrahedrons, each having a volume of V by 6. Okay, so if I have any general 3D object, okay, that's the last time we were talking of a simple connecting rod. Okay, I can split this connecting node into a set of cubical elements, and each cube I can split into a set of tetrahedrons. Okay, and for each tetrahedron we know how to get the local stiffness matrix and the local force matrices, and then we can use it in the global matrices. Okay. Any question on this part? Okay. In that case, we will now go on to some other elements, typically two-dimensional quadrilateral elements. Earlier we have seen a simple quadrilateral element consisting of 4 nodes. Okay, and we said that for this 4-noded element, let us say we define a zeta coordinate as zeta equal to -1 here, and zeta equal to +1 here, and eta equal to -1 here, and eta equal to +1 here. Okay, so we converted the xy coordinates into zeta eta coordinates, and then we defined the 4 shape functions n1, n2, n3 and n4 using these zeta and eta coordinates. Okay, and then we also mentioned that in a element like this, if we have to find out the local stiffness matrix K, we have to carry out integration using numerical techniques, because the integration would involve terms of zeta and eta which have to be integrated over the element. Okay, this was for a simple 4-noded element. Now instead of a 4-noded element, we can have an 8-noded element. We can have 4 additional nodes like this. Okay, the advantage that we will have in this, that if you remember earlier when we were talking of a one-dimensional problem, we had a 2-noded element and we were doing linear interpolation between these 2 nodes. Then we went for a 3-noded element and we said we will do quadratic interpolation between these nodes. Okay, similarly now we will go for an 8-noded element and we will try to do a quadratic interpolation. Okay, the way we will define an element would be something like this. We consider 8 nodes like this, and let us say at node 1 we will define zeta equal to -1 and eta equal to -1. At this point we will get zeta equal to 1, that means zeta is varying in this direction, and eta will vary in this direction, that means along this curve we will get eta equal to 1. Okay, so this point will be the point -1 1, this point will be the point 1 1. Okay, and typically if zeta is varying from -1, eta is varying from -1 to +1, here you will get eta equal to 0, so this point will be -1 0. Okay, at this point zeta will be 0 and eta will be -1, so this point is 0 -1, and at this point zeta is 1 and eta is 0, so you will get at this point to be 1 0 and this point to be 0 1. Okay, 1 0 0 1, all these are in terms of zeta and eta. Okay, so now if you have the 8 nodes, we have to define 8 shape functions. Okay, so the 8 shape functions again they will have the same constraints, that n1 will say will be 1 at node 1, will be 0 at all the other nodes. Okay, so n1 will be equal to 1 at node 1 and 0 elsewhere. Okay, similarly for n2 and so on. Okay, so let's redraw this element in terms of the zeta and eta coordinates. So okay, so there are 8 nodes. Okay, this is 1, 2, okay, and if you have to define a shape function, let us say n1, which is 1 at this node and is 0 at all the other nodes, we will first draw straight lines. Okay, the equation of this straight line would be 1 minus zeta minus eta equal to 0. That means along this straight line you will find zeta plus eta will be equal to 1. Okay, you can verify it at these 2 points, zeta plus eta will be equal to 1. Okay, similarly if you consider this straight line, okay, this will have the equation 1 minus zeta plus eta will be equal to 1. Okay. Similarly, this line will have the equation of 1 plus zeta plus eta equal to 0, sorry. Okay, so zeta plus eta will be minus 1 along this, and similarly along this edge, okay, this one we will get 1 plus zeta minus eta equal to 0. Okay, basically for all these 4 lines we have 2 points and I am writing down the equation between the two, equation of the line between these 2 points. Okay. Now if I consider node 1, for node 1 I want n1 to be 0 at all the other nodes. Okay, so I will consider, let us say this straight line, okay, this straight line and this straight line. So I consider these 3 straight lines and I say that n1 will be 0 at all these 3 straight lines, that will ensure that n1 will be 0 at all the other nodes. Okay. So that would mean that n1 will say that n1 will be of the form some constant multiplied by the equation of this straight line is 1 plus zeta plus eta. Okay, so it's the 1 plus zeta plus eta. The equation of this straight line, okay, this straight line, okay, the top one is eta equal to 1.
Why don't we take this shape function to be simply Lagrange polynomials?
Okay, again,
we can take these shape functions to be simply Lagrange polynomials.
the shape function can be defined in any way. The choice is totally up to the user. Okay, you can take shape functions according to any formulation as long as they meet a particular set of conditions. Okay, so we can take it this way, we can take it in any other way, there is no problem on that. Okay, the only thing that will change would be the stiffness matrix that you will get. Okay, so this n1 will say will be some constant multiplied by 1 plus zeta plus eta multiplied by the equation of this line, that will give us 1 minus eta, and similarly this vertical line will give us 1 minus zeta. So if I take my n1 to be of this form, okay, then we can ensure that n1 will be 0 at all these nodes except at node 1. Okay, and then we have the condition that at -1 n1 is equal to 1. So I put zeta equal to -1, eta equal to -1 in this equation. Okay, we will get n1 which is equal to 1 will be equal to c times, I am putting -1 here, so we will get -1 into 2 into 2. So that means c will be equal to -1 by 4. Okay, so n1 will get it in this form. Similarly, we can take n2, and for n2 we will say that we will consider this vertical line. For n2 we will consider this vertical line, this horizontal line, and this inclined line. Okay, for n3 we will consider this vertical line, this horizontal line, and this inclined line, and so on. Okay, for n5 I will consider this vertical line, this horizontal line, and this vertical line. n6 I will consider these 3 lines, and this way I can get all the 8 shape functions. Again, once I have the shape functions, the process of getting the stiffness matrices and the force matrices would remain the same. Okay, we will again carry out the same integrals. We will need numerical techniques for evaluating the integrals, and we will get the stiffness matrices. Okay, any questions up to this point? Okay. Next, let us see that if we take an element which is a 9 noded element now, we take an additional node in the center. Okay, so let us say okay, so if you look at this point has coordinates of -1 1, -1 1. Okay, let us say this has -1 1, this has 1 1. Okay, this will have 0 1, this has 1 0, this will have 0 0, this has -1 0. Okay, this will have 1 -1, and this will have 0 -1. Okay, and now we need to define 9 shape functions for this. Again, these are the zeta and eta values. Okay, so these values are zeta and eta. I am redefining my x and y in terms of zeta and eta. Okay, so for an element like this, what we will do is we have to define n1, n2, so on till n9. Okay, the way we can do it is we will define one line like this, another line like this, and a third line like this. Okay, in this direction what is changing is zeta, and in this direction my eta is changing. Okay, so we can define 3 functions, L1, L2 and L3. Okay, if you remember, in a simple quadrilateral 3 noded element, in this element we had said n1, N2 and N3, we have taken quadratic variations for this, and for N1 we had mentioned that this will be minus half of zeta into 1 minus zeta. N2 we said would be 1 plus zeta into 1 minus zeta, and N3 we said would be half of zeta into 1 plus zeta. Okay. Now what we will do is we can look upon this element as just an extension of a one dimensional 3 noded element in the second direction. Okay, that means we will consider this line to correspond to a function L1, this line to correspond to a function L2, and this line to correspond to a function L3. And similarly, we will consider a function along this line, and along this line. Okay. So what we will do is, analogous to this, we will define L1 of zeta to be minus half of zeta into 1 minus zeta, L2 of zeta to be 1 plus zeta into 1 minus zeta, and L3 of zeta to be half of zeta into 1 plus zeta. Okay, that means L1 is defined along this line. Okay, so L1, this is 0 at zeta equal to 0 and zeta equal to plus 1. Okay, so if I consider this line is zeta equal to minus 1. This line is zeta equal to 0, and this line is zeta equal to 1. Okay, so if I consider L1, this is 0 at zeta equal to 0 and zeta equal to plus 1. So L1 will be 0 at this line as well as at this line. Okay, while at this line L1 will be equal to plus 1. Okay, so L1 will be equal to plus 1 at this line. Okay, similarly L2 will be 1 at this line, will be 0 at this line and at this line. Okay, and L3 will be 1 at this line and 0 at both these lines. Yeah. Okay. Similarly, what we will do is we will define another 3 functions L1, L2 and L3 along in the vertical direction. Okay, so we consider vertical direction. We draw a separate figure. I'll again draw the element as a rectangular element. Okay, so we have defined along this edge, we define L1 of zeta which is equal to 1 along this edge and 0 at both these edges. Along this edge we have defined L2 of zeta to be equal to 1, and along this edge we have defined, here we have defined L2 of zeta and here we have defined L3 of zeta. Okay. Similarly, we will define along in the vertical direction L1 of eta, L2 of eta, L3 of eta and L2 of eta. Okay, this is equal to 1 here, this is equal to 1 here and this is equal to 1 here. Okay. Now the shape function for the point 1, okay, which is n1, will define n1 to be equal to the product of L1 of zeta and L1 of eta. So L1 of zeta multiplied by L1 of eta. This way I will ensure that n1 will be 1 at this point, will be 0 at all the other points. Okay, if I take n2, I will take n2 to be a product of L1 of zeta and L2 of eta. Okay, and so on. For n5, okay, I will write it here, n5 will be a product of L3 of eta and L1 of zeta. Okay. So this way for all the 9 points I can write the shape functions as a product of L1, L2, L3 of zeta and L1, L2, L3 of eta. Okay, so for point 9 I will take the product of L3 of zeta and L3 of eta. That will ensure that it is 0 at all the other points. Okay, and again once I define the shape functions, the process of finding out the stiffness matrix and the force matrices remains the same. Okay, so in any element, the basic thing is to find out the is to specify the shape functions for the element and define the element accordingly. The stiffness matrices, force matrices, etc. can be found out by a process of integration, which we have already seen a number of times. Is that okay? Okay, the basic advantage that one gets of taking elements which are either 8 noded or 9 noded, the basic advantage is that if I have three nodes along an edge, I can do a quadratic interpolation along that edge. Okay, that means earlier when I was having a simple 4 noded element, okay, my 4 noded element was like this. So the edges have to be defined in a linear manner. I cannot get curved edges. Okay, similarly my stress and strain patterns will also be equally restricted. I am doing linear interpolation everywhere. Okay, so for 4 noded elements I have to have straight edges, but for an 8 noded element I can have curves like this. And so on. Okay, so extra nodes on the same element will give you more flexibility in defining the element. Okay. Similarly, we have seen a triangular element. Okay, and we have defined a triangular element lies 1, 2 and 3 nodes. We can also define a 6 noded triangular element. And again we can define 6 shape functions for that. Again, one way of defining these shape functions is that along each edge you have a parameter like zeta, eta and phi. Okay, so zeta, let us say, is varying in this direction, eta is varying in this direction, and phi, let us say, varies in this direction. Okay, let us say this is 0, maybe 0.5 and 1, again eta is 0, maybe 0.5 and 1, and again phi is changing as 0, 0.5 and 1. And again the 6 shape functions can be defined in a similar manner. For node 1 I will consider this straight line and this straight line. Okay, for node 2 I will consider this straight line and this straight line, and so on. Okay, so this way we can define a 6 noded triangular element also. Okay, and the same ideas can also be extended to 3 dimensions. Okay, right now we have talked of a 8 noded quadrilateral element. Okay, we can define a cubical element. Okay, first we can define an 8 noded cubical element. Okay, then we can define a 20 noded cubical element. At the center of every edge we can have an extra node, and so on. So 12 edges that give us extra 12 nodes. You can have a 20 noded cubical element. You can also have a 27 noded element. At the center of every face you have an extra node. 6 faces plus the center of the cube. You can have a 27 noded cubical element. Okay, but then you have to define the 27 shape functions accordingly. Okay, the basic process can be the same. Okay, any questions up to this point? Okay, then I will stop here. In the next class we will consider how to generate a mesh from a given object. Okay, how to generate a mesh automatically for any kind of element. Okay.